All right, welcome ladies and gentlemen. This is our gases video number 2. So make sure you have your notes open to that. In this video, I'm going to be talking about something called gas laws. What are they? And then the big gas law that we want to know, something called the combined gas law. So first up, what is a gas law? It's a relationship. Basically, it's comparing changes that happen to gases like a before and after. How do the conditions of the gas change? If you vary temperature, how does pressure change? And we've already done work with that in class with the activities we've been doing. But a gas law, it takes this statement of what happens and it makes it into an equation. It's a formula. So it makes it mathematical where you can legitimately calculate what will happen because you change something about the gas. So this allows us to make these relationships quantitative that we've been discussing in class, how pressure changes with volume, etc., etc. So first up is Boyle's law, and Boyle's law is about the relationship between pressure and volume. And as you've worked out, hopefully pressure will increase as we decrease volume if we keep our temperature constant, and that's Mr. Boyle right there. And this is actually the formula. So this is right here, this is the gas law. P1 times V1 equals P2 times V2. The 1 and the 2 mean a before and after. So this is the P1, V1 would be your initial pressure and initial volume, and your P2, V2 would be your final pressure and your final volume. And this is our indirect relationship, if you remember. Pressure goes up as volume goes down. And again, the reason why, as you've worked out, if we have a small volume, then the gases don't have a lot of space, so they are colliding with the walls a lot more frequently, and the pressure is going up. Versus if there is a large area, if there's a high volume, then they're not hitting one another nearly as often, so the number of collisions are going down. So we have our indirect relationship. And I would like you to please add this graph into your notes. You're going to sketch that in, because this is the graph that shows that indirect relationship. We have volume on the x-axis and pressure on the y. Notice pressure is in kilopascals. And if we have a very small volume, something close to the origin on the x-axis, then when we go up and we go over, we have a very high pressure. Versus if we have a very large volume, something really far out on the x-axis, and we go up and we go over, we have a very small pressure. So we have that indirect relationship. Next up is Charles' law, and that's Mr. Charles right there, and this is the relationship between volume and temperature. All right, volume and temp. And this is saying that if you're increasing the temperature of a gas and you are keeping the pressure constant, so like think of a balloon, think of something that can actually change its volume. You increase the temperature of a balloon, you're going to be increasing the volume of that balloon. That balloon is going to get bigger. And this is our gas law for Charles' law. V1 T1 equals V2 T2. Again, this is a before and an after. And notice, though, that we're dividing, so V1 over T1 equals V2 divided by T2. And again, the balloon example is a great one. That's what this picture is really showing. So this is on the left. This is very cold, so it's a low temp, and the balloon is smaller. And then as we increase the temp, if we put it on a hot plate, the gas particles are speeding up, so they're going to be colliding with the walls of the container, and they're going to push the container out higher, and the volume is going to get larger. So this is a direct relationship between temperature and volume. And again, once again, I'd like you to please sketch this graph in, so you're going to add this in, and this is our graphic representation of this. We have temperature. Notice, ooh, that's going to be super important. Temperature in Kelvin is on the x-axis, and then it will be volume on the y-axis. But again, this is our direct graphical representation that as the temperature gets higher, so does the volume. They're increasing together. And then next is Gay-Lussac's law. And there he is. And this is the relationship between pressure and temperature. And again, notice that we're kind of keeping the other thing constant. So if we keep volume the same, so if you have something like a rigid canister, a steel drum, something that can't really change its volume, if you increase the temperature of the gas, you're going to be increasing the pressure on the inside of that system. And this is our gas law. Again, it's the before and after. The 1 and the 2 for P1, P1 and P2 mean before the change occurred and after the change occurred. And once again, this is a direct relationship. As one goes up, the other also goes up. We are dividing, though, in this case. And again, please add this graph in, sketch this graph into your notes. We have temperature again in Kelvin on the x-axis and pressure on the y-axis. This one, our pressure is in kilopascals. If we're keeping volume the same, so volume not changing here, at a low temperature, our gas particles aren't moving very fast, so they're not going to collide with the walls very often or with much force. But as we increase the temperature, now the gas particles are moving very fast, and so they're going to be hitting the walls of the container very frequently and with a great deal of force. So our pressure is going to be going up. Now, critical thing about using the gas laws. When we are doing these calculations, your temperature has to be in Kelvin. You are not allowed to use Celsius temperatures when using these calculations. There is a reason for that, because Kelvin has no negatives. 0 Kelvin is the lowest temperature we can get to, and it's not actually possible to get all the way down to 0 Kelvin. Well, the reason that we want to use a temperature scale with no negatives is because if you think about these calculations, these formulas, right, it's pressure and volume and temperature. And if you had a negative temperature value, like you could have in Celsius, then that would mean you would be solving, you could possibly get a negative volume. And that can't happen. You cannot have something that takes up less than 0 space. We cannot have negative volumes. Likewise, we cannot have negative pressures. Something either is exerting pressure or it isn't. It's not exerting negative pressure. So we need a temperature scale that is never negative, because all the other things we're talking about are also never negative, right? Pressure's not negative, volume isn't negative, so we need a temperature scale that isn't negative. So if we ever see Celsius given to us in a gas problem, we have to convert it to Kelvin first before we do any further calculations. So this is a huge point, and I'm going to trick you out. I'm going to be testing you to see if you're remembering to do this many times. So really make sure you're paying attention and you're converting your Celsius temperatures to Kelvin. Now, there's a whole bunch of all these different gas laws, right? Charles' law, Boyle's law, Gay-Lussac's law. Do you have to remember them individually? No, you do not. And the reason that you don't have to remember them all individually is because of something called the combined gas law. And the combined gas law is P1V1 over T1 equals P2V2 over T2. And this is the one that we're going to be working with. This formula, it incorporates all 3 of the gas laws. For example, if you were to cover up temperature, then you have Boyle's law, P1 times V1 equals P2 times V2. And if you were to cover up, let's say, pressure, P1 and P2, you'd have Charles' law, V1 over T1 equals V2 over T2. So this is a combination of all the gas laws. And this is the one that is on your reference table. It's on table T, where all our formulas are. It does assume that the amount of gas is being held constant. We're not changing how much gas is in the system, but we are altering things like pressure and temperature. And this is a huge point. We don't always have to have pressure, volume, and temperature given to us in the question. If one of the things is being held constant, then you simply remove it. It cancels out of the equation. It would be like saying, okay, so if we have pressure and volume changing, but temperature is staying the same, it would kind of be like pick a temperature that you want, let's say 100 Kelvin, and keep T1 and T2 at 100 Kelvin. If it's the same, you can sort of just take it out of the equation. But you must have temperature in Kelvin when you're working with this equation. You cannot use Celsius. No Celsius. Celsius bad, and we're certainly never going to see Fahrenheit in these problems. So we're going to just conclude with a sample problem with the combined gas law. A steel canister with a fixed volume is initially at STP. Calculate the new pressure of the canister if the temperature changes to 50 degrees Celsius. So to start this problem, we really kind of want to figure out what the information is that's been given to us. So we have a steel canister with a fixed volume. So that's actually going to be important. So volume is fixed. That means volume is constant. That means volume is not changing. So we're going to be working with that. Is initially, well, that's another word that means a before, right? Initially means before. And it's initially at STP. Hey, what's STP? STP is a set of conditions right? STP means numbers. It means specific numbers. So initial slash before, we're actually going to be setting up two columns. We're going to be setting up initial and final slash after. And initially we know that the gas is at STP, so I'm going to write that down. It says calculate the new pressure. Calculate the new pressure. That means that we want to find out what the new pressure is. That means that P2 is our unknown. That means that P2 is our X. Of the canister, if the temperature, oh, they gave me information about temperature, changes to 50 degrees Celsius. So that means that the final temperature must be 50 degrees Celsius. But I can't leave that in Celsius. I have to convert that to Kelvin because I need that absolute Kelvin scale. So converting that to Kelvin, I get 323 Kelvin. So this is basically, notice that two columns, an initial slash before and a final slash after, and I'm breaking down what it is that the problem has given me. So I know that the volume is staying fixed. So in the formula, P1 V1 over T1 equals P2 V2 over T2. Because the volume is staying the same, I'm going to actually remove it from the formula. So I'm actually going to get rid of it right now. I'm just going to erase it and rewrite it. Because if the volume isn't changing, then I don't need to calculate anything with that. And the formula now becomes P1 over T1 equals P2 over T2. So the volume stayed the same, so I legitimately got rid of it. If you wanted to like pick a volume, let's say 1 liter, 1 would be a great number to pick. You could actually plug that in for V1 and V2. Looking at the question, it asks me to solve for P2. So this is our X, right? So that means we must know everything else. But notice it didn't give me numbers for P1 or T1. So that's going back up to our initial. All it told me was that initially we're at STP. Well, STP refers to certain temperatures and pressures. So what temp and pressure does it mean? So we need to look it up on table A. So standard temperature is 0 Celsius, but remember, we want it in Kelvin, so we're going to use the 273 Kelvin. Likewise, standard pressure is 1 atmosphere or 101.3 kilopascals. Now, this problem doesn't specify a unit to use for pressure, so I'm actually going to use the kPa one because we tend to say a lot of kilopascals in Regents chemistry, but you could certainly also use the 1 atmosphere one. So just for this problem, I'm going to be using 101.3 kilopascals. But again, STP means numbers. They gave you T1 and P1. You just have to go look them up on table A. So now I have P1, I have T1, I have T2, and I know that I'm solving for P2. So now I'm going to just plug in and solve. So setting this up, I have 101.3 kPa over 273 Kelvin is equal to, I'll put in X for P2, divided by 323 Kelvin. Okay, I'm just going to erase some stuff so I've got some room to work. Now solving this, you want to solve for the unknown. So remember math class, this is where you want to do your bow tie thing, your cross multiplying, right? That's what we're going to be doing. So I'm going to multiply 101.3 times 323 Kelvin. When I do that, I get 327 19.9. I'm keeping all the numbers for now. I'm only going to round at the end. And then you're multiplying 273 times x. Right? We want to solve for x. X is here. So that means dividing by 273, right? We want to get rid of that 273. So I'm going to divide both sides by 273. When I do that, I solve for x. And remember, x is P2, which is what the problem is asking for. And I get 119.853, blah, blah, blah. Looking at sig figs, there are 3 sig figs in this number. Again, there is a decimal. That means we're coming in from the left. So the zeros that follow are actually significant. So I want 3 sig figs in my answer here. So I want these 3, but I am going to round. And the way I can round this and still have 3 sig figs, I can do 120 and then I can add a decimal, and then I don't need anything that actually comes after the decimal. That's enough to make that significant. And then what unit would it be? Well, this is pressure, right? But so I go back and I look, what pressure unit did I use in my calculation? I used kilopascals. So that would be the pressure unit, and that's going to be P2. So we're going to be practicing a lot with this in class because there's a lot of different ways to do this type of calculation, but that's just one example.